course Education Economics. Now we're in a block where we will discuss methods that are very relevant in education economics. And actually they're relevant not just in education economics but well beyond. In other fields of economics, but also in many other disciplines. We will focus here on methods for causal inference. Thank you. So when I was working with education scientists from, who were not economists but who were from other disciplines, and we were also discussing what are the contributions of the different disciplines to the overarching field of education economics. And one point that economists can contribute to that are the methods for causal inference. And that's what we will do. I think economists can also have other very important contribution to the broader field of education science. This includes budget constraints. Many disciplines don't really, they talk about the benefits, but not so much about the cost. So economists always, someone has to pay for it. Who should pay for that? In general, what are the consequences of different schemes offering? And then kind of also what economists do a lot is to link education, that it's not just standalone, but to later life outcomes, particularly when it comes to the labor market. And with Victor Ulakov, you have already kind of discussed some of this relations between education and the labor market outcomes in the form of returns to education human capital. One distinct contribution of economics to this broader field of education research, education science, is methods, and particular methods for causal inference. So what we will do today is that we will start with a short primer and causal analysis. Here I would be very much interested in what you have already experienced during the course of your studies. Then we will focus on one strategy to identify causal effects in particular, which will be also kind of the main part of today's lecture, namely randomized controlled trials, or RCTs, where it's the researcher who assigns individuals randomly to whether they receive a specific intervention or whether they don't receive it. But it's kind of the researcher who decides based on the principle of randomness who gets that. And we will see what are the advantages of this procedure. Then you will see some studies in the economics of education where these randomized control trials are actually and then we will conclude with some thoughts about concepts of internal and external validity. And here, my assumption is that your background is quite heterogeneous, but I would be very much interested in kind of what are aspects that are really new for you, and what are things that you have heard like 3 or 4 times, because then we can skip them if everyone has heard that one. Okay, so, and I mean so officially this is a lecture, but we're a very small group, so make use of that chance so we can ask, when you can ask questions, we can come to this discussion. So in empirical social research, there are 3 main areas. There's description, there's prediction, and there's causal analysis. All 3 parts are very important. Description just describes how the world is. So that's about like inequality in education. So if your mother has a university degree, how high are your chances to obtain university education yourself compared to if your mother does not have university education? That's a purely descriptive question, but it's a very important question. And there are many important descriptive questions like that. Prediction is also a very important field. This is something where machine learning is very strong. If you have enough data, then many potential predictor variables. This is something where the field of machine learning opens up kind of very superior methods. And then you can economics like we often have to do with prediction to admit them could be in principle that you predict on their likelihood of success. You want to predict whether someone is likely to complete the studies, and then you want to admit those students who are likely to pass. That's a prediction. And then there's kind of this third block, which is causal inference. And this is what we will focus on today, and also in the next sessions, because this is kind of really where contribution of economics comes into this education. And here the questions are, what is the effect of X on Y? Does obtaining a university degree increase your wages, increase your future satisfaction, your chances on the level? Does decreasing the number of students in a high school or in a high school class, does this positively affect learning outcomes? So that learning outcomes are better in smaller groups. So there are many questions like that. Does it pay off to attend early childhood education? Or does it harm children when they're taken away from their mother at age 3? And these are kind of causal questions, and here we'll get to know some tools that are relevant in this third. So we'll focus on this. But these other two, description, prediction, are also very important. What for you as a student and also as a researcher, when you write your thesis, so it's important to make clear in which of the areas are you with your research question. Is it a question about causal inference? Then you should apply causal inference methods. If your goal is prediction, then kind of the tools that you apply might be very different. And then the question, or the research question that you have, some of them are inherently causal or non-causal, and you should be aware of that. Because what I've seen a lot, not just by students but also by researchers, is actually that they confuse it. So they have a causal inference research question, but then they say, oh, they just talk about associations, about correlations. But in the end, then they give kind of some policy recommendations which are based on kind of a causal story in mind. So that's I think not very helpful because that's not really transparent and not really fair. It can be even harmful. Or when you have a descriptive research question. So when you're interested in like the example that I gave, whether the mother has university degree or not, what tells that about your chances on average to have university degree yourself, that's a descriptive research question. So that's interesting in itself. But at that point, we're not saying it's because the mother has the university degree. But it can also be completely fine if that's because the mothers who raised university or have mothers who have a university degree, they might be very different in many aspects from those that don't have a university degree. So there might be kind of some selection, but for the pure description, this is not relevant. So you don't need to care about this kind of selection bias. Okay. So we will focus on causality, and here's like a motivating picture of why causality is important. Causality is important when you want to change something. And the scriptures we just described are good, but if you want to change something, you need a causal story in mind. So think of this picture here. So there's a truck that does not move forward. So it's stuck. And then there's kind of this guy in front has several friends, and they're all kind of willing to help. And then the guy in the front is set in front, like 1, 2, 3, and everyone really pushes as hard as they can. The guy who is here standing on top of the truck, he's the strongest guy. He's pushing really heavy, and he realizes whenever I push, the truck moves. And of course, you know a bit about physics. It's not the guy up there who's moving because he's standing on the truck. But he sees the correlation. Whenever I push, the truck moves. But this is not the causal story. He's not moving that. You could say, okay, this is a bit funny. Stupid guy who's not doing that. But now nothing. Okay, they're counting 1, 2, 3. Everyone pushes, but the truck is not moving. Yeah? So what's the driver in the front seat supposed to do? Well, he should think about how can we improve that? And if he has the right causal model in mind, you would say, guy in the red shirt, please climb down and also push the truck from behind, because that's the only way that's happening. Yeah? So here, by taking a correlation for a cause and effect, we're wasting resources. And in the worst case, we're not kind of achieving the goal that we actually want to achieve. So therefore, it's important to distinguish between correlation. This is the correlation. The guy pushes, the truck moves. And the cause and effect. The truck moves because the guy pushes. I mean, that's not just about truck driving or getting a stuck truck to move, but that's also kind of in many areas of economics, but also in social science in general. So, when I was a student myself, in my master thesis, I investigated the relationship between income and longevity, so life expectancy. And I focused on women for some reason, and I found out women with higher income, they have a higher life expectancy. So they live longer. So that's a purely descriptive finding. But I found it interesting in itself. I was not the first to show that. But now let's think, okay, this is a correlation. It happens at the same time. It doesn't mean that it does not necessarily mean that they live longer because they have the higher income. Might be very different. And now think about like a policymaker who wants to improve longevity of individuals. And says, oh, well, we just have to, we take this correlation for cause effect, and we just hand out money to the poor people. And then they will live longer. It might work, but it might also not work. Because he's taking the correlation for cause and effect. But it might be that it's not the income that's driving this difference, but it might be that there's education. Education improves income, and education also improves longevity. In the sense that you know more about, that you can read medication, that you can know more about risky health behaviors and the dangers of that. So many things can be related to education. And that's I mean, it's just an example right now, but it could mean that we hand out money to the poor in order to improve longevity, but it does not pay off. Actually, it might get worse, because let's assume do people buy cigarettes and alcohol from that which even decreases the longevity. So this is just an example. So it might well be that the income increases longevity. But my point is we need the right causal model and the right methods to identify causal effects in order to have the right policy. Otherwise, we will not achieve the goal that we wanted to achieve. And might even have negative consequences of what we actually wanted to achieve. Okay. Who has heard about the potential outcomes framework, or the counterfactual framework, or Google causal model? None? Okay. Are you all asleep? Good. But still some people who are asleep, they can rest. Okay, so that's interesting. Okay, but then we can talk a bit more about that. Because I was not sure. Because I think this is kind of something that's covered in several courses. And I think this is also very important because this counterfactual framework, or is it also known as the potential outcomes framework, is the dominant approach for causal reasoning. For thinking about causality and for expressing different strategies to identify causal effects. And as the name counterfactual framework suggests, counterfactual situations play a crucial role. And the causal effect is defined as the difference between two states of the world. One actual state of the world and a counterfactual state of the world. So let's assume we're interested in what's the effect of you having a master's degree on your future earnings. Then, kind of at some point we can observe your income when you have a master's degree. But what's counterfactual, what we don't know, what would be your earnings if you did not have a master's degree? And you can see already in the language that I'm using, it's expressing this counterfactual. So what would have happened? So this is a thought experiment at that. But come with me to this thought experiment. So we say the cause effect of the university degree is comparing your income, if you have the university degree, to you at the same point in time if you did not have the university degree. And this difference between these two, it's called potential outcomes. So potential outcome with treatment, with a university degree, without the university degree. So the difference between these two potential outcomes, that's the causal effect of the master's degree. So that's a thought experiment. But this is kind of a helpful thought experiment because it directly puts us to the main problem. One of the situations is counterfactual. We can't observe. So we say the causal effect is the difference between this and this. That's very easy to compute if you have this and this. But now what I'm saying is only one of the two states is observed. For individuals who do not have a master's degree, we know their income without master's degree. But what we don't know is what would be their income if they had a master's degree. So also for them we can't compute this difference. And this is known as the fundamental problem of causal inference. So there's a fundamental problem. We don't know what the counterfactual situation is, so we can't compute the causal effects. And this is now where different strategies to identify causal effects come into play, because they try to somehow construct the counterfactual based on different assumptions. So one takeaway message from this is we need assumptions for causal inference. And what's worse, for each causal identification strategy, there's an assumption involved that we cannot test. So what I'm saying is, whenever there's causal inference involved, we need to make assumptions that we cannot test. Therefore, all causal inference is uncertain. And this is a different type of uncertainty compared to sampling uncertainty. That's what we usually deal with in statistics. So we have a population that we're interested in, but we only have a sample. And then we want to make conclusions about the population. That's sampling uncertainty. That's a different type of uncertainty. But here, we have uncertainty about the counterfactual state. And therefore, all causal claims should be somehow modest, because there's always uncertainty involved on whether the assumption that we're making holds or not, because we can't test it. But it doesn't mean that all approaches on causal inference are equally valid or not, just because we need to make assumptions. Some assumptions might seem way more reasonable than other assumptions in a given context. And what we will do, you will get to know some strategies for causal inference. Today, we have randomized controlled trials. In 2 weeks, and in 3 weeks, and in 4 weeks, and we'll get to know other strategies for causal inference. And whenever I say a strategy for causal inference, a strategy always comes together with an assumption. And this key assumption that cannot be tested is called the identification assumption. That's the assumption that we need to believe in order to give our estimations a causal interpretation. So, and you see by the wording that I'm using, it's belief. It's not a proof, it's a belief, whether the assumption holds or not. Of course, kind of good research tries to make the assumption more plausible. And we will also discuss ways of making the identification assumption more plausible, but we can't prove it. So we can make it more plausible, but we can't prove the identification assumption, so we can't prove that we identify a causal effect. So therefore, kind of this terminology of proving, that comes to mathematical proofs, but not to when it comes to causal claims in the social science. We can't prove it. We can just support these assumptions. Okay. Let's introduce some formal notation. I'll try not to use too many formulas here. But sometimes I find mathematical expressions very, very helpful because they're more precise than the verbal language that I'm using here. And so now I gave you like one explanation, like a more verbal explanation. Now it comes kind of the more mathematical explanation, but I try to limit it. And I try to attach it to an example. So let's assume we're interested in the effect of class size on learning outcomes. So in education science, there's a long-running or long-standing debate on what's actually the best class size for learning. So it's a bit about university education, but mostly in secondary, so in school education. So is it better to be in a class of 15 or in a class of 70 or in a class of 30? Kind of most people kind of would assume, okay, the smaller the better. But it's not so easy to identify this causal effect. But let's assume this is kind of now what we're interested in. And now we're simplifying things for now. We're assuming that the variable in whose effect we're interested in is binary. So it can take on only two values. So there's either a small class or a large class. This is just to make the exposition a bit simple. This potential outcomes framework is flexible enough to take like on many value treatments, continuous treatments, but we kind of reduce complexity. So there's small class or large class. And that's called our intervention variable, or as I would call them, the treatment. I would call that treatment no matter whether it's in a randomized controlled trial, so like in a medical trial where someone gets a medicine, like a pill, or not. But we use the term in line with the literature, treatment to always refer to the variable in whose effect we're interested. So here we have a treatment variable denoted by D, which is taking the value 1. If someone's in a small class, and the value 0 if someone is in a large class. So D is a binary variable, 1 has the treatment, in this case small class, 0 is in the control treatment, in that case a larger class. And then we're interested in our dependent variable, Y. And that's assuming that's in our example, it's a standardized test score at the end of the school for student I. And whenever it's about causal inference, I would call this dependent variable outcome. So later on the left-hand side of the equation, you have the outcome. On the right-hand side, you have the treatment. When you think about an equation, then you might have some control variables for specific strategies. But that's kind of the way we have the treatment, and that's the variable in whose cause and effect we're interested in, and Y is the outcome, and how we measure the effect of the treatment. Okay, then we now come to a formal definition of a causal effect, for an individual I. We call that causal effect delta. And delta is, as I just described verbally, the difference between two potential outcomes. So you see, there's both times yi, but one time with an index of 1 and the other time with a super index of 0. So 1 is the potential outcome under treatment. So that's so if D is equal to 1 and yi 0 potential outcome under no treatment. So here d is equal to 0. And this is just the mathematical expression of what I just explained. So the cause effect is defined as the difference between two states of the world. When one where the treatment is applied and one where the treatment is not applied. So in our example, yi1 would be the standardized test score at the end of the school year for student I, if the person was in a small class. And y0 would be the potential outcome, so the standardized test score, the same student, if she was not assigned to a small class, if she was in a large class. So that's just kind of verbal interpretation of this problem. Mostly, we're not interested in the individual treatment. So we're not interested in the causal effect for student I, because that's even more difficult to identify and estimate. What we are usually interested in is some kind of average treatment. And here I wrote down the formulas for the two most prominent average treatment effects. One is called ATE for the average treatment effect, which is just basically, it's just the mean of all the individual treatment effects in the population. And this is kind of written down using this expectation operator. Are you familiar with the expectation operator? Because that should be in a minute. So that's just the expectation. You can think of this as the population average. So the average treatment effect, as the name says, is basically the average effect over everyone in the population. And then we have the ATT, which is also an average treatment effect, but not for everyone in the population, but for those who receive the treatment. And sometimes this ATT is what we're mostly interested in, and sometimes we focus on the ATT because we can identify it with fewer assumptions. So they're different. Sometimes they focus on the ATT, sometimes on the ATE, depending on what we're interested in or what we're more likely to be able to identify. So think about, we're interested in the effect of hospital on health, going to the hospital. And now, kind of, in that case, maybe we're interested really more in the ATT. In the effect of hospital for those individuals who actually go to hospital, on health outcomes. Because we're not interested in the effect of hospital treatment for healthy people. We wouldn't go to the hospital anyway. I mean, there might be some reasons to focus on them as well, but often the focus is we want to know, does hospital make people healthy? And that's why we focus on the ATT. And that's basically, it's also the expected value of the individual treatment effects, but only for those in the treatment. And we can pull this further apart. Then we have the expectation of y1. I'm skipping this. So that's the difference between the expected value of y1 minus the expected value of y0. Sorry. This one should be, of course, 1. Both times for individuals in the treatment group, those who receive the treatment. And now when you look at this way of formulating it, you can directly see this one is counterfactual. So for individuals in the treatment group, it's the expected outcome if they were in the control group. There's a 0 up here, but a 1 over there. So this is counterfactual. You can observe the first part, but not the second part. So identification strategies, they try somehow to construct or estimate the second part based on some such correlation. is not in a small. So for Emma, we observe y1, but y0 is counterfactual. Whereas for Leon, we observe y0, but not y1. The cause and effect is defined in the same way for both of them. So you see, instead of the I will wrote once here the E for Emma or the L for Leon. But in both cases, we can't compute the counterfactual. In both cases, we can't compute the cause and effect, as in this last column, because in the first case, this one is missing, and in the second case, in Leon's case, this one is missing, is counterfactual. This is the fundamental problem of causal inference. Okay. Now, in this slide, I want to discuss the difference between correlation and causation. I'm sure that you have all heard something like, from correlation it does not follow causation. Correlation does not imply causation. So it's not the same, but this does not really help to understand what's the cause and what's causality. Okay, here, let's assume there's a correlation. Namely that students in smaller classes often have worse test scores than students in large classes. This is a correlation, just a description. Let's take it as face value for a moment. So this could mean, well, there's indeed a cause and effect. That being in a smaller class is bad for your test score. Maybe, I don't know, in smaller classes, you do not benefit from your other students very much. So maybe the smallest class that you can think of is a class of size 1, where it's just you and me. So maybe that might be very, very bad for students who have been just with the teacher. Maybe it's better to have. So there might be an idea why there's indeed this cause. But most importantly, just because there's this correlation, we cannot infer on the causal effect, because there might be two things which might be very harmful for causal interpretation. The first one is reverse causation. And that's reverse causation, meaning the causality is actually running in the opposite direction. So it might be that students with bad test scores are put in smaller classes. And I think that's also kind of a reasonable case. So if you're the headmaster or the principal of the school, and you want to assign students to different classes, and then you want maybe to put more effort, more resources into worse students so that they manage to cope, and then put them in smaller classes. That would be here an example for reverse causation. So test scores affect whether you are assigned to small or to large. Another issue could be what I call confounding. There could be a third factor that affects both our treatment and our outcome rate. And that's kind of a very common problem in many observational studies, that there might be this confounding, this lurking third factors or variables. In our example, so it could be that school quality is that. And so there might be what I call colloquially bad schools. So bad schools receive more funding because the government wants to help the worse schools or whatever. Or worse students, or schools with students who have more learning difficulties. So bad schools receive class size because they have this additional funding. But at the same time, bad schools reduce learning. Or when this was a confounder at the school level, but it can be also a confounder at the individual level. So there could be students with learning difficulties, or students with bad social behavior. So who always interrupt the teacher in class, and the headmaster, the school planner puts them in smaller classes because then it's easier for the teacher to handle these students who do not behave well in class. Yeah? So, on this slide, we established that just because there's a correlation, it does not mean that there's a cause and effect. Yeah? And the reason is there could be reverse causation, so the cause effect going in the other direction, or there could be confounding. Yeah? This confounding is there's a third factor, so that might be school quality, or that might be social behavior of the student that affects both the treatment and the outcome. And we don't know whether these exist or not. In theory, they can exist, and just because there's a correlation, it doesn't mean that there's a causal effect. So we must reconstruct the counterfactual in a credible way to answer the causal question. Okay, I think I already mentioned this. So you can also think of this fundamental problem of causality as a missing data problem. We either observe Y1 or Y0, the outcome under treatment or the outcome under no treatment. Okay. Now there are different strategies to identify cause and effect. Actually, they're just like a handful of causal inference strategies, which I find very motivating, because it's not that there are like 1,000 strategies to identify causal effects, but if you know about these identification strategy, you know basically the general idea of the most common identification strategies. And of course, within each identification strategy, there are kind of different versions how to implement. But the general idea, the general identification assumption is the same within one of these classes of identification strategy. And in this course, you will actually get to know all these identification strategies. Today, we will talk about randomized controlled trials. In 2 weeks, we will also talk about difference and difference. We will talk about instrumental variables and about regression discontinuity designs. But today's focus is on these randomized controlled trials. And this is what we will do now, unless there are any questions from your side. So kind of key takeaway messages. So the most common way to think about causal effects is this counterfactual framework. Where we say causal effects, the difference in outcomes between the observed and the counterfactual situation. This directly shows the fundamental problem of causal inference that we can't just compute. And this gives all causal inference an air of uncertainty. And now these identification strategies, they somehow try to construct the counterfactuals in a convincing, hopefully convincing way. But still, we can't prove causality. We can just transparently mention the identification strategy and then try to put additional evidence that this assumption is likely to hold. Okay, so RCT is maybe the most well-known strategy to identify causal effect. Randomized controlled trial, RCT. Here it's the researcher who basically flips a coin, and based on the coin flip, assigns the one person to the treatment group, the other to the control. Whatever the treatment here is. Why is that so powerful for causal inference? Well, the idea is because it's a coin flip. The 2 groups, the treatment, the control group, are in expectations identical. So we expect that before we conduct the experiment, we assume the treatment control group will be the same, because it's a coin flip who decides whether someone comes to that group or someone comes to that group. So for those of you with some basics in statistics, you can see this as basically drawing 2 samples from the same population. We draw one sample, that's the treatment group, and the other sample is the control group. If it's a random sample from the population, we basically assume that in both groups we converge to the population parameter. So before we conduct the experiment, we assume that treatment control group will be very similar, even identical, if it's a large sample with respect to the control group. So of course, in small samples, when we have, let's say, just 10 individuals in the treatment and the control group, there might be imbalances. But the larger they get, the smaller the imbalances get, and most importantly, there will not be any systematic differences. It could be, even if we have just 10 in treatment and control group, before we conduct the experiment, there's no assumption to believe that in the treatment group there will be more males. Or the ratio of males will be higher than in the control. And this is what makes these RCTs so powerful. Because we have two groups who are essentially, or can be assumed to be the same. And then the idea is, let's say the treatment group receives the treatment, and then the control group shows what would have happened to the treatment group if they did not get the treatment. And because we're saying that the control group and the treatment group are basically identical, just that the treatment group receives the treatment. So the control group serves to construct the counterfactual.
So the only difference in different models then that they are randomly assigned to the treatment and control group? Or
Yes.
Is it?
Yes. And the second difference is that here for RCTs, we do not need to observe, we can work with cross-sectional data.
Okay.
So in the difference, we need to measure our outcome at different points in time.
Okay.
And here, one would be sufficient. But in fact, many RCTs also have measured the outcome at baseline. But from an identification perspective, that would be necessary. But the crucial element is really that it's assigned based, the treatment is assigned randomly, which is not the case in the difference group. So you have heard about difference and difference. Okay, now let's make again use of a bit more formal notation. So here is the identification assumption in mathematical terms. This sign means it's orthogonal to or independent of. So what it says, it's the treatment is independent of the potential outcome. We're not saying of the realized outcomes, not of yi, but of yi0 and yi1. These are the potential outcomes. So just by knowing whether someone is in, we can focus on the first one. So yi0 is orthogonal to the treatment. So that means without the treatment, we assume that the treatment and the control group have the same distribution of the outcome value. That's kind of what we assume here. And this is kind of the most general independence assumption that we have. Actually, for the computation of the ATE and the ATT, so the average treatment effects, we just require a slightly weaker version, which is this mean independence assumption. So whenever the full independence up here is satisfied, also mean independence is given, but not just because mean independence is given does not mean that the full distribution is given. So for mean independence, it does not follow general independence because the mean is just kind of focused on the mean. Okay, but I find the mean independence assumption a bit more intuitive. So for the ATT, we were interested in this counterfactual situation. We wanted to know what would be the outcome for individuals in the treatment group if they did not receive treatment. So this was a bit in, like a purple color. This is counterfactual. So we don't observe it. But in RCTs, well, we say it's equal to this letter. And the idea, kind of what we say is, the outcome under no treatment is on average the same for individuals in the treatment group than for individuals in the control group. This is an assumption that we're making. But because of this, it's maybe an assumption that we're willing to believe if randomization works. Similarly, we assume for individuals in the control group, we don't know their outcome under treatment. We don't know what would have happened if those individuals who do not have a master's degree, if they have a master's degree. But we say, okay, it will be the same as for individuals in the treatment group if they receive the treatment. That's an assumption that we're maybe willing to believe with randomization. What I want to show you on this slide is, once we are willing to make the assumption, then it's just simple mathematics to show that we then can identify and calculate the cause and effect. But this is the assumption that we need to make, that we can't prove. Once we're willing to make this assumption, then it's kind of easy to show that the observed difference in means here is equivalent to the ATT. And that's kind of what we show here. Okay, let's go step by step. So here it's EYI, so that's the observed outcome for individuals in the treatment group. And this is the observed outcome for individuals in the control group. When we don't have an RCT, then this does not usually not work. But here, let's go one step after the other. So that's the observed difference. And now can we say, okay, the observed difference means it's Y1 for individuals in the treatment group and Y0 for individuals in the control group. So far, no assumption, no magic involved. Just kind of a rewrite. What we do now is that we make use of this first part of the mean independence assumption. We basically plug in this equation to the next slide. And there, we basically exchange the latter two terms. So these two are exchanged by assumption. Just plug it in. And then we have here the formula for the average treatment effect on the treated. And what we can further do in RCTs, because it's randomization, we can show mathematically that we don't need to condition on d equal to 1. So that means that the average treatment effect in general is the same as the average treatment effect on the treated and the same as the average treatment effect on the non-treated, AT&T. And that also intuitively makes sense because we randomly assign individuals to the treatment group and to the control group. Basically, what happens in the treatment group is also what would have happened in the control group if they received the treatment. Therefore, these average effects are the same in both groups. But that's just the second most important part. Really the crucial part is that by making this assumption, we can calculate the average treatment effect and the average treatment effect on the tree. Because that, so that was the mathematical expression. Kind of the more intuitive expression is really the two groups are the same, the treatment and the control. Basically the same. Just that one group receives the treatment and the other not, based on the principle of random. And therefore, the control group shows what would have happened to the treatment group if they did not receive the treatment. That's the idea. Okay. One can also show causal research questions and causal identification strategies using causal graphs, whereas they're called directed acyclic graphs, DAGs. So this is a DAG. Directed acyclic Directed means they always have these arrows that point in one direction, so they can't point. So this one would not be a DAG. It's not a DAG, but points in two directions. Acyclic means that there are no cycles. So that's a cycle. But they don't exist in these DAGs. We would model them differently. And graph means it's a graph. So this is just where the name comes from, the causal graph. So they're very helpful to illustrate identification strategies. So I will also make use of them. D is our treatment variable. And we're interested in the effect of D on Y, our outcome there. The problem is now they might be confounding. This is just confounding third factor called X. And now, when we see a correlation between D and Y, this might be because of this actual causal effect, but it might also be because of this confounding due to X. And in the language of this directed acyclic graphs of the causal graph, we say there's a backdoor path. We can go from D to Y, both on this direct path, but we could also go using this backdoor path, dxy. And now the idea is basically to eliminate all these backdoor paths. And I will show you what an RCT does. This is what an RCT does. In observational studies, X would be a predictor of D, or X would have an effect on whether you get the treatment. So think of bad social behavior. So when students with bad social behavior, they're more likely to receive the treatment. They're more likely to be put in smaller classes. That would be the confounding. But now the RCT eliminates this correlation or this effect, because it's randomly assigned who receives the treatment or not. So students with bad social behavior, they will be both in the treatment group and in the control group, and to kind of the same extent, at least before we conduct the experiment. And this is what RCTs do, not just for one variable, for X, but for all potential confounders. Those that we can observe, but also for those that we can't observe. This is the strength, the power of the randomized control trials. That's also the reason why these were kind of the weapon of choice for testing the efficiency of, for instance, COVID vaccination. This is exactly how it was done. So when it was tested. So participants who volunteered to participate Yeah? Some of them randomly got like the true vaccine that was supposed to be tested, and others got just some other injection, yeah? So that they did not know in which group they were. Yeah? And then kind of these pharmaceutical companies, yes, together with their university partners, they follow basically the two groups. Yeah? And then they checked how many COVID infections did we have in the one that got the vaccine, and how many COVID infections did we get in the group that did not get the vaccine. And then they compared the rates to determine the effectiveness of the vaccine. Yeah? So this is kind of standard in medical research, yeah? But we can also use it in social science research, yeah? But not always. Yeah? And we will come to the downsides or the shortcomings of RCT. Yeah, but that's kind of the general idea that we have. And COVID, vaccine testing, and the idea was, okay, was based on the principle of randomness, who got the true shot and who got kind of a placebo. So we assumed a priori the two groups were the same. So the one group showed what would have happened to the other group if they were in the opposite treatment. And all kind of correlations were eliminated. Okay. RCTs, they're very common, not just in medical research, but also in web development. And I don't know whether some of you have heard about A/B testing. That's kind of extremely common in web development. So for instance, you're very likely to be part of many experiments at the same time whenever you open your browser, basically. Because the tech companies, they kind of play around whether a specific button is blue or red. That's kind of the treatment. And then they kind of count the variables that they're interested in, how often you hit that button and go to advertise. And then you can have, of course, not just A and B, two groups, but you can have crossovers, many things tested at the same time. But all of these are actually randomized controlled trials. They're just that here we always talk about two treatment arms, so a treatment and a control arm. But many RCTs are way more complex. But the basic principles are just, so we could not just test whether small class or large class, but we could have classes with small, medium, large, or classes with 10, with 11, with 12, with 13, with 14, with 15, with 16 students, and so on. That's at least how we can think about it. Then, in terms of RCTs, it's important to distinguish between two different types of experiments, namely field experiments and lab experiments. Lab experiments is shorthand for laboratory experiments. Laboratory experiments are RCTs carried out in highly controllable environments, laboratories. I don't know whether you participated in some experiments by psychologists or economists here, because here at the Free University we also have these labs. And often you can sign up there, and then you receive some money for participating. And then you don't know often you don't know what the research is about, but often you will receive some treatment or some control, but you don't know in which groups you are. And so laboratories doesn't have to mean that they're people with this white colors, but it's outside of that as well. Then field experiments are randomized controlled trials that are carried out outside of the laboratories. So think about COVID vaccination. I would say this was mostly a field experiment at the final stages. Because the individuals, they couldn't live their normal lives. So the outcomes were measured, so whether they got affected or not, in real world settings. They did not have to stay for 3 months in a specific campus where that was tested, so in a specific laboratory. But that was a field experiment. Both have their pros and cons. Field experiment, it's just important to know the difference between these two. Then they're also kind of different in designs. So there's some RCTs where even the same subject, the same individual, gets different treatments. That's called the within subject. RCTs, they are often seen as gold standard for causal inference. And I think they're very, very good, very strong, it's very helpful to have them in the toolbox for causal inference. However, they also have, just because someone does an RCT does not mean that they actually identify the true causal inference. And there are many reasons for that. First of all, there might be dropout. So individuals decide no longer to participate in the RCT. And this could be kind of selective in the sense that this differs between treatment and control group. For instance, some colleagues of mine from Bochum, they conducted an RCT with obese individuals. So individuals with where their body mass index exceeded like some high values, and then kind of the research team provided financial incentive for weight reductions. Then they had a control group that did not receive any financial incentive, and then there were two treatment arms. One received, I don't know, €100 if they met a specific weight reduction target, and the other received 200 or 300 once they met. And in that, of course, the researchers could not force the individuals to participate or to show up for the weight measure. But what they saw is that in the control group, way fewer people showed up for measuring the weight, for measuring the weight, because they had no incentive to do that. So there was kind of this follow-up. There was selection bias that induced, because those who met their target, they were way more likely to show up. And in the control group, there was less incentive actually to show up in general. So the researchers then had some strategies to cope with that, but this is kind of where more complicated statistics and econometrics came in. For an RCT, you don't need any complex statistics or econometrics methods. It's a comparison of means. You take the mean of the treatment group and the mean of the control group, and then you compare these two means, and that's the average treatment. That's not very complicated for the statistics. So when you have a very good design for causal inference, then the math behind it is very simple. The statistics based. Just when the design is more complex or has more problems, like this non-random participation in the follow-up, then we need to use more complex statistical methods. But for causal inference, it's usually design trumps statistical analysis. So when you have a better design, that's way more credible than the best statistical complicated method that we have. So I see kind of statistics then only as a remedy. In case something does not work out as expected or is more complicated than expected, then we use it. Then we can use these methods to make the best, to get the best possible, or come, if it's not the first best, then it's the second best. And get to the best possible solution there. Okay, we will try to discuss internal and external validity at the end of this lecture. But just maybe a short information. Internal validity refers to whether we are able to identify a cause effect for the population, for the group that we actually study. And in that respect, RCTs are often very good. Because it's kind of rather, this assumption is rather credible, but it's not so clear how can we generalize these findings to the general population. And this is called external validity. Internal validity, can we identify causal effects, credibly identify causal effects for the study sample that we have? External validity, how can we generalize the results to a broader population? And this is also something where RCTs might have weaknesses, but the main weakness, in my view, of RCTs is I would like to conduct them, but I can't. For ethical, for financial, or for political reasons. So I would like to run an RCT in Germany where I really test whether being in a small class improves student outcomes in the lab. But this would mean I randomly have to assign some of the students in smaller classes, some in larger classes. And this would not be feasible in Germany for political reasons in that case. Because they would not let me experiment with their students. Often it's not political reasons, but it's more ethical reasons. So in well, think about returns to education. What's the effect of a master's degree on your earnings? An RCT would mean I randomly assign master's degree to some students and randomly assign no degree to other students. That would be the perfect RCT. That would kind of give very strong evidence for what's the cause and effect of a master's degree, but it's ethically not feasible to do that for good reason. That I cannot randomly assign individuals to have a master's degree or not. Or in my PhD thesis also examine the effects of unemployment on health. An RCT here would mean that I randomly make people unemployed and randomly keep others in employment. It's also not feasible for good reasons. So therefore, this is in my view, the strongest disadvantage of RCTs. It's very good to know them as a benchmark, but for many research questions that we're interested in as social science researchers, we simply can't conduct for ethical reasons. But nevertheless, I think it's very important to have them in the toolbox and also use them as a bench for causing. So therefore, it's not enough to just know about RCTs. You also need to have knowledge about other strategies to identify causal effects. But there might be some situations where RCTs are feasible, and I will give you some examples now from applied research in education economics, so that you also get an idea how and where this can be implemented. So here I'm showing you one of the most famous RCTs in education economics, and it's called Project STAR. And that was actually an experiment on kind of this example that I had on class sizes. It was conducted in the US state of Tennessee, and STAR stands for Student-Teacher Achievement Ratio. It was a randomized trial in the 1980s in Tennessee, where in about 80 schools, more than 11,000 students participated. And there were kind of 3 treatment arms. Small, regular, and regular plus some teaching aid. And students were really randomly assigned to one of these 3 groups. And so already kind of think about this, how logistically difficult that was to set up this. So that was when kind of students applied to schools, the schools need to participate, and then kind of the schools need to be kind of forced to go either to small or to regular special cases. However, they did it, and due to the random assignment, the treatment is assumed to be independent of potential outcomes. So in all 3 treatment arms, the share of black students should be the same. The share of female students, the share of individuals from low or high social standing should be the same. Also, those with behavioral issues by randomization should be, at least before we conduct the experiment, should be identical or similar across the groups. Okay. Here they or at the beginning we make again the point that class size is endogenous. Meaning there might be this confounding due to some unobserved confounding determinants of learning. And I gave you some examples. Here, in the US, they found that smaller classes are often found in wealthier areas or better funded schools. So here there could be more the example that we find that in smaller classes, there are students with better test outcomes. But here also, the same as before, it's not clear whether it's due to the class size or because it's better, well, they live in wealthier areas anyway. So there might be parents who are more affluent, so they can have better needs to think about due to this randomization, the observed difference in test scores can be interpreted causally. Because we say, okay, the two groups are the same, and the experiment reconstructs the counterfactuals. What they found in Project STAR is that students who were randomly assigned to participate in smaller classes, they scored higher on standardized tests. And then they found some effect heterogeneity, so that students from disadvantaged backgrounds and minority students benefited the most. And then additional research kind of looked at the long run consequences, and they found that it does not affect just in during school or in the early years of school, but actually there are higher graduation rates and also better scores in this university admission test in the US. So kind of the conclusion was that smaller classes can causally improve student learning outcomes both in the short and in the long run. And here put some key references. So you see this was 1990, the earliest that there was in educational research. So Erziehungs this in Germany journal, but then also economists jumped on this, particularly for the long run outcomes. So Alan Kruger here is in the QJE, so Quarterly Journal of Economics, paper 1999, but also Russ Chetty in 2011. And Coles, they look at the long run outcomes. And I told you in the beginning that one contribution of economists to the broader field of education research is the focus on causality. But another contribution is also the focus on the costs, so budget constraints that we have, and who should afford the funding. So here, kind of what one would have to do as well, and what was also done, was kind of a cost-benefit analysis, because kind of decreasing class size is very expensive. So kind of basically if you reduce the class size by half, you need to employ twice as many teachers as you do. And teachers are kind of the most important, or very crucial point in kind of a part of the education budget. So you won't have to kind of balance the cost and the benefits of that. And here was basically established the benefits. But because there are these long run effects, it seems very likely that at least here, I mean, we're talking about reducing, let's say, from 22 to 26 to 13 to 17 students, that this might be still beneficial. Because if there are higher graduation rates and also maybe higher university admission rates, then this could pay off by the higher taxes that these individuals pay. So this is something that a full cost-benefit analysis would have to take into account. So far we talked about the benefits of that program, but I think this is already kind of a very important milestone step. Okay. So this was a very famous example. Now I'll come to some more recent examples to give you more ideas where RCTs can be done. And this is a study of some of my colleagues in the core office from the University of Potsdam, where they randomly distributed e-book readers to families from more disadvantaged backgrounds. And the idea is that kind of observational, we see that children from high SES, so socioeconomic status families, they're way better in reading than students from low SES families. So there's reading early on, and that starts already before school. So that's a description of learning. And this is kind of a relevant gap, because reading is very, very crucial. So if you can't read, and you will also not be good in math, because there often you need to read text. It will be way more difficult for you to acquire additional skills, like English language, because for that you also need to read. So reading is really like a basic competency, and if there are gaps between more affluent and less affluent families, then this is kind of problematic, because it all starts very early and has long-run consequences. So low-income children, why do they have worse reading skills? Well, they read less, maybe because they have limited access to books. Maybe if they read not so very helpful books, and maybe they're just very far away from public libraries. So if they live in worse neighborhoods. And now the question is, can randomly provided e-book readers, together with curated book recommendations, increase reading engagement and then long-term academic performance of the students? And this is kind of what this research, this is a very current project, what they test. So what they did is, they sampled 1,000 children from low-income households in Germany at the age of 11 to 12, so that's the beginning of secondary schooling in most German states. And then students were either randomly assigned to a treatment or to a control group. About 500 children in the treatment group then received e-book readers, where they had a 1-year access to a library of about 1,000 books. And then they received monthly book recommendations. Then there were several follow-up students where both individuals in the treatment group and in the control group, who did not receive the e-book reader, where there were kind of surveys conducted. That was like a half a year, 1 year, and then several years later. And what they find is the provision of e-book readers increases the reading frequency and the number of book reads. But it's not just that students read more, but it really improves their reading comprehension. And that's not just relevant for reading, but it also has positive spillover effect on other subjects in class, in school, like math. And here, kind of, they did this kind of cost-benefit analysis, cost-effectiveness analysis, and then they found, okay, providing an e-book reader is rather cheap intervention compared to the benefits that you have in the law. And then if you want to read more about it, so you see, this is a very recent discussion. Okay, then the last example that I have is actually from my own research, because I've used this lecture also to make some promotion for my own work. None of you were in my bachelor's statistics courses, right? At some point, because then I try to engage students regularly with the material, so I have to teach statistics 1 and statistics 2, and both are mandatory, compulsory for our undergraduate students in economics. And for many students, it's not the subject that they love the most. It's called statistics. So when you shake your head, you can't understand this, I can't understand it either, but that's what students told me there, that this is not their most favorite subject. And many kind of start learning just at the very end, so toward the exam. But I think statistics, because the material builds on top of each other, it's really crucial to follow from the beginning to the end. Because when you don't get the basics, then it will be very, very difficult to to get like the further steps. So what we try to do is to engage or to make the students engage early on in with the material. We can't force them, but we can set incentives. We talk about incentives. Yeah? So the students could participate in some tests that we design. And when they were successful, they could receive some additional points for the exam. That was kind of what we did. And then we worried a lot about cheating. We wanted to test, and we wanted to that they engage in statistics, but we didn't want to increase cheating. So we applied different measures, and one measure that we applied is that we changed the order of the questions, so that not one test was the same basically as the other test. Because so there was a different sequence of, so everyone received the same, that's 20 or 25 questions, but in a different order. So that not two students sitting next to each other that they could copy. But then we worried, oh, maybe this is unfair. Maybe this is unfair because some students will start with a very difficult question, and others will start with a simpler question. Those that start with a difficult question, we just want to put them under time pressure, again, to mitigate cheating. So if you have like a bad start, maybe then you get nervous, and then also in the follow-up question, the next questions you perform worse. And then once we had done this, we realized actually what we did here is an RCT. It's a randomized controlled trial where we randomly assigned individuals to having a difficult first question or a not so difficult first question. And then this is what we did. We did this at different universities over many years. And then we looked at whether starting with a difficult question or an easy question improves overall performance in the test, or affects overall performance in the test. So this is a so-called zero effects test. So where we find starting with a difficult or an easy question does not have an effect. So there's a zero effect that we have. So usually as a researcher you're always happy when you find significant effects. Here we were on the one hand disappointed, on the other hand we were also very happy, because it means that randomly changing the order of the questions does not impact overall test performance. So we argue that the randomization of test order, test questions, is cheating without harming the outcomes in the long run. This is one plot that I bring because as one way to convey the results. So first of all, I showed you, okay, the treatment is difficult versus not difficult question. It's not so easy to determine what is actually a difficult question, what is not a not difficult question. So what we did is we said, okay, we can't decide it, but let's the data do that. And we basically checked for every question how many students answered that question correctly. And then took this as a measure of the share of the students who correctly answered that question as a continuous measure of question difficulty. Took away the one person that we were interested in to construct that. And then we tried to not only have this continuous treatment, but also to make it more binary. To say, okay, and then we say, okay, the first 50% so we ordered the questions by difficulty, and the first 50 were then counted as difficult questions, and the other 50% as not difficult questions. And that's what you see when you get the median split. The third p-side split, we say, okay, the top 30% of questions are difficult questions, and the other 70% are the non-difficult questions. And we did the same with the second p-side, the first p-side. And then you see here several dots. Yeah, every dot is basically like one test that we did. So in one test there could be usually between 100 to 300 students who are behind that. And this is the effect size. And you see, this basically is what you can see is the 95% confidence interval. And you see here are the effect sizes. And you basically see that no point estimates are outside of these confidence intervals. Up here there's like 1 or 2, but that's kind of what we would expect. And as there was a zero effect as well, just due to pure luck. Yeah, so what I want to convey with this is, sometimes we have a slight positive, sometimes a slight negative point estimate, but in general there is no effect on overall test performance. Okay, and we can directly link this to internal and external validity. So internal validity is with respect to the study population that we look at. So here, it would kind of be, internal validity would be hampered if, for instance, students who started with a difficult question were more likely to be from high SES or low SES. SES is always socioeconomic status. But because we randomly assigned it, we started with a difficult or simple question. There should be not this kind of selection. It should not be related to that. And we also checked it with some of the variables that we have available. But what about external validity? And this is what can we learn from our setting for all other settings. And here, this is way more difficult to show. Because I mean, we did it with students in our courses, but these students are not a random sample from the overall population. They are our students. So strictly speaking, we can only talk about it. And then kind of this is what we discussed then as the limitations. It was kind of testing at university. So it does not tell us anything about testing at schools later in life. And also here there was some incentivation so that students could earn points for the final exam, but it was also not a very high stakes situation. And so it was not that people would die. Let's say if they did not get 100% in that test. And this is kind of meant by external validity. What can we learn from a setting at hand to other settings? How can we generalize them? And this is very, very difficult to achieve. And usually kind of, so what we try to answer that is, well, we did it in different subjects in different universities, to have at least a broader perspective. So that to say, okay, maybe our results can be more generalized to the university. But that's just arguing. So what would we have to do is actually would have to, from our population, draw a random sample, and then in this random sample, randomly allocate some to the treatment and some to the control. This is very often not feasible. So most studies focus very much on internal validity. That at least for the study population, they get an unbiased estimate of the true causal effect. But that means we should always have this external validity in the back of our minds. So what can we learn from the research finding in this specific setting for other settings? Whatever other settings. And I think I will. I uploaded these slides. I think this discussion of internal and external validity is very crucial. Also, knowledge about them. So read about them. What I said is basically the main essence of internal and external validity. Okay. You can also check the summary on causality at home. think this is kind of just my way to summarize the many key takeaways from what we discovered in the lecture. Also here, a summary on ICTs and internal and external village. And so my recommendation would be that after this lecture, we go through these slides again, so that we really recapture what we did here. We just in 2 weeks or 3 weeks time when we discuss these other strategies to identify cause and effect, we'll come back to the issues that we discussed. If you want to read more about it, here I put also some suggested readings. Here for the introduction, if you're very new to this field, then this is highly recommended. This is more if you want to do your master thesis or your PhD.